Hi everyone, this is Dr. Diana Songsong again, and we are now on our third part of mathematics in efficiency. So recall that we already had linear programming, assignment problems, and transportation problems. So we will now be discussing shortest path problems. That problem there that is solved by Google Maps for us is actually an application of a branch of mathematics known as graph theory. First, what is a graph theory? Graph theory is a study of graphs, which are mathematical structures used to model pairwise relations of. Okay, what is the origin of graph theory? This actually came from this problem. This map here that you can see is Königsberg, now known as Kaliningrad in Russia. In the early 1700s, people from this town posed a particular question. And this question is this: is it possible to take a walk through town, crossing each of the 7 bridges just once and ending up wherever you started? Now, this is actually hard. It just looks simple, but when you try to look at it, it's actually hard. And the famous Swiss mathematician Leonhard Euler heard of the problem and solved it. He actually solved it, and the answer is no, it is not possible to do that. In the process of finding the answer, he invented graph theory. Okay, so the question here is, okay, what we will do is we will turn the bridges into edges, and then the land masses, we will turn that into points. So that's your first point. That's this land, and then that one. Okay, so we're just turning all of our land masses into points. And then the bridge, that will be represented by an edge. Okay, meaning to say, this is the bridge connecting this land to this land. Okay, and then what else? This one. Okay, next, this bridge, and then this bridge. What else can connect this, right? Oh, this one first. This one, what else? This, and of course, this edge here, this bridge. So that's connecting this point to that point. Okay? So now the problem can be viewed as this. Can you draw the diagram without lifting the pen and without tracing lines more than once? Okay? Let us first discuss a few terminologies. Undirected graph. An undirected graph G consists of two sets, the vertex set and an edge set. The vertex set is the set of vertices and the edge set is the set of edges. What are edges? Edges are just lines that join two vertices. So, for example, here we have a graph and our vertices. So, our set V of G would be the set A, B, C, D, E. And our edge set, they are edges. So that's AB, AC, BC, DC, and CE. Okay. When do we say that two vertices are adjacent? If they are joined by an edge. This edge is denoted by UV. Just like in this case, we have an edge. This is the edge AB, AC, BC. So meaning to say A is adjacent to B, A is adjacent to C. Okay? Order and size. What do we mean by the order of a graph? It is just the number of vertices in G, whereas the size is the number of edges. So going back again in our example, the order of G is the number of vertices. And how many vertices do we have? We have 5 vertices. And what about the size? We are just counting the number of edges. So that's 1, 2, 3, 4, 5, 6. Okay. Next, multiple edge and loops. If there is more than one edge joining vertices U and V, then G contains a multiple edge. So for example, here, look at vertices D and E. There is more than one edge joining D and E. This edge, and this edge. Okay? So we say that DE is a multiple edge. Okay? What do we mean by a loop? An edge from a vertex U to itself. So for example, here we have a loop. It started at A and it ended at A. If a graph contains multiple edges or loops, we say that the graph is a multigraph. So otherwise, it's called a simple graph. So this graph that we had earlier, this is a simple graph because it doesn't contain multiple edges, right? Whereas this is a multigraph because it has multiple edges, and it has loops. It has a loop at A. So for this course, we will only be discussing simple graphs. What do we mean by degree and neighborhood? The degree of a vertex, okay, it's denoted by this. It's just the number of edges that are incident to the vertex U. So meaning to say how many edges are coming out of the vertex. So if you have a vertex like this, you have 3 edges coming out of it. That means that it has degree 3. What do we mean by the neighborhood of U? It's just a set of all vertices that are adjacent to U. So for example, in this case here, what is the degree of our vertex A? Our graph is G. How many edges? 1, 2, right? What would be the neighbors of A? So since the degree is 2, it has 2 neighbors. Those are B and C. Is that clear? Whereas, for example, C. What is the degree of C? It's 4 because it has 4 neighbors. A, B, D, and E. Okay, walking on a graph. What is a walk? A walk of length K is just it's just a sequence of vertices such that 2 consecutive vertices are joined by an edge. So for example here, so this is a walk. A, B, C, D. That is a walk. So A, B, C, D. This is a walk of length 4. Oops, I'm sorry, of length 3. Okay, so we're actually counting the number of edges. Okay, and then what do we mean by a path? Okay, a walk is called a path if all the vertices are distinct. So this one, the walk that we had earlier, A, B, C, D, is actually a path because all of the vertices are distinct. What do we mean by a cycle? It is a cycle if you started and ended at the same point. So for example, A, B, C, A. That is a cycle. A, B, C, A. That is a cycle. Okay. Connected graphs. A graph is said to be connected if there is always a path from a vertex to another. So this graph here is actually connected because if you just get any two vertices, you can always get a path, right? From one vertex to another. Okay, so for example, D and E, they're connected by a path. C and B, I can go through B, A, C. All right. What about a disconnected graph? This is an example of a disconnected graph. For example, if I take vertices 11 and 14, there is no path that will take me from vertex 14 to vertex 11. So that's why this is disconnected. Whereas the previous slide is connected. Okay, what do you mean by a weighted graph? We will actually be dealing with this weighted graphs. If edges are assigned with numerical value, so for example here, the edge 1, 4 has a numerical value or weight of 5. The weight of edge 1, 2 is 2. Understand? Okay, a directed graph. What about a directed graph? It consists also of a vertex set and an edge set. However, the only difference is that you have direction. So that's why it's called a directed graph. Okay, and you write it like this, and it will we call we do not call this edges, we call this arcs because AB, because we have an arc AB, but we do not have, oops, maybe that should be capital A. We have here AB, but not BA. Understand? Because these are arcs. You have only one direction. But similarly, the order is the number of vertices and the size is the number of arcs. So again, the only difference for directed graphs is that the edges are no longer called edges, they are called arcs. Okay? But of course, in this course, we will not be discussing directed graphs. We will only be discussing simple graphs. Okay, now this I don't know how to pronounce it, Dijkstra's algorithm. What we want here, this is a tool that we use to determine a shortest path from a starting vertex S to any destination vertex. And it applies to all connected simple graphs, directed or undirected. Although again, for this course, we will only be looking at, my examples will only be using undirected graphs. Okay, but this algorithm will also work for directed graphs. So how does it work? Okay, so let me now illustrate Dijkstra's or Dijkstra's. Let's just say Dijkstra's algorithm. Okay, so first we will start at vertex A. Wait, let me just write here. A, B, C, D, E. Okay. We will start at vertex A. Of course, the distance of A to itself is 0, right? So let me just write that 0. Okay. And then when I write a box, that means that that is my current vertex. So remember that when I have a box, that means that is my current vertex. Okay, meaning to say I have already visited it. Okay, so once we have visited a vertex, we now look at the vertices adjacent to it. So in this case, that's B and D. Now from the graph, what is the distance of B from A? So the distance of B from A is its weight, which is 6. So we write that here. And the distance of D from A is 1. 1. And of course, under the previous vertex column, we visited B via A, right? So for both of them, previous vertex is A. Understand? Okay. Now, let me just write those numbers. So the distance of B from A is 6. The distance of D from A is 1. Now, what is the next vertex that we are going to visit? We will always visit the vertex that has the smallest distance. So since that distance is 1, D is closer to A, right? Because this is 1, this is 6. So my current vertex now is vertex D. Okay? So now, my current vertex is D. I will do again the same algorithm. I will look at the unvisited, meaning to say the vertices that do not have squares on the distances, right? So what are the adjacent vertices to D that we haven't visited? So that's B and E. I will no longer include A because A is already visited. There is already a box here. Understand? Now, again, the vertices adjacent to D are B and E. We will now write the distance. Now, this one here tells us that the distance of D from A is 1. So what is now the distance of E from D? So it's 1 plus 1, correct? Meaning to say that's 1 plus 1 there, okay? So I will write the distance of E from A now is 2. Is that clear? Because that's 1 and then 2. Okay? And then, how about B? So B now, its distance via D that's 1 plus 2. So this one now becomes 3. Understand? So I will erase that because that's smaller. Okay. I will now update my column. Now this B, the distance now of B from A is 3. Previous vertex is D, right? And then E, the distance is 2. Previous vertex of D. Is that clear? Now, what do we do? Once we have these numbers, we again look at the vertex which has the smallest distance. So, get the smaller number. So, that's 2. So, we now box 2. Okay, so meaning to say E is my current vertex. Okay, now let's look at again the vertices adjacent to E that that are that do not have the squares on them. So that's B and C only. Correct? Okay, so what will be the distance of B if we use this E? So that will be 2 plus 2, that is 4. But I already have 3 here. So I will not update this because I already have the smaller number. Okay? So I will not change that to 4 because 3 is smaller than 4. And then the distance of C from A is 2 plus 5. So that's 7. Okay. So I will update my column. So the distance of C is 7 via vertex E. Correct? And then for B, I did not update it. Okay? Because 3 is smaller than 2 plus 2. Okay? And then same again, we look at the neighbors and then choose the smaller number. That is 3, right? So we now box 3 and we look at the vertices adjacent to B that we haven't visited yet. And in this case, that's only C, right? So what is now the distance? So via B, so it's 3 plus 5, 8. But this is already 7, so I will not update that. Understand? So this one still remains to be 7. Clear? Okay. And of course, so that's the last. Of course, we will now visit 7 and we have no other option. This is now the smallest number because it has no competitor. That's the end of the line already. Understand? So meaning to say the shortest path, this table here actually tells us the shortest path of all the vertices from A. So this one is saying that, of course, it's obvious here that you know what will be the distance. The distance of C from A is 7, the distance of E from A is 2, and so on. But what is the importance of this previous vertex column? So here's how it goes. Actually, for the distance of A to E via what path? It's obvious, right? It's A, D, E because it's short, right? However, I will show this to you. For example, what is now that path from A to C of length 7? So what we do is we go backwards. So from the table, C, the previous vertex is E, right? The previous vertex is E, okay? But from the table, what is the previous vertex? D. So we write D. Again, from the column, what is the previous vertex of D? That's A. And that's exactly what we want. So our path is A. So there, I will highlight it using red. So that's A, D, E, C. And that is now that 1 plus 1, 2 plus 5, 7. Of course, it's possible that you can easily see that because we're just dealing here with a very small graph. But of course, it will be very much complicated when we will be dealing with larger graphs. Okay? Okay, so let's have another example. Find the shortest path from vertex S to all other vertices of the given graph. Okay, so let's have our table again here. So from vertex S, distance of course is 0. So I will put 0 here. This is my current vertex. And the adjacent vertices, wait, I should write down my vertices. I have S, A, B, C, E, F. Okay, all right. Now, my adjacent vertices are A and E. And then let's write the distance. The distance of A from S is 3. And this one here is 4. Correct? So distance of A, 3, E is 4. Previous vertex is S, right? Then what do you do? Choose the smaller number, which is 3, and then you box it. Okay? Now, again, look at the neighbors, which are not yet boxed. So that's B, F, and E. Correct? Okay, so let's see. What would be the distance of E if we pass through A? So that's 3 plus 6, 9. But I already have 4 here. So this remains unchanged. Okay? 3 plus 6 is 9. That's bigger than 4. So just 4 remains here. Next, what about B? So that's 3 plus 2. So the distance is 5. Next, of F, so that's 3 plus 7. So that's 10. Okay, let us now write that. So B5, F is 10. The previous vertex A, 8, right? And then again, we will look at the adjacent. And what will we box? The one with the smallest number. So in this case, that's E. So that's 4. Again, we look at the adjacent vertices. So that's F, F only, right? Because we no longer, oops, by the way, this is a directed graph. Okay, so am I doing it correctly? Yeah, okay. So meaning to say you cannot go back. You have to follow the arrow. Anyway, Uh, where am I? Okay. So for vertex E, the only vertex, so meaning to say it's not adjacent to A, right? Because this one only. Okay. So that's 10. I mean 10, not F, the vertex F. What will now be the distance? 4 plus 5. So that's 9. So this one gets updated. So this becomes 9. So F here becomes 9 via vertex E. Okay. All right. So, um, again, we look at the numbers, the unboxed numbers. And the smallest now is 5. So we now box 5. Next. Again, we look at the adjacent vertices. Okay, so that's C and F. So here, what will be the distance? So 5 plus 8. So this is now 13. And then here, 5 plus 1 is 6. 6 is smaller than 9. So that means we found a shorter path. Understand? So that becomes 6. So we will now write for C, the distance is 13. Previous vertex is B, right? And then for F, now the distance is 6. I will erase that. So this is 6 and previous vertex of B. Is that clear? Okay. And then again, we look at the smallest number between the smaller number between the unboxed numbers. So in this case, we box 6, right? And then the only remaining adjacent vertex that is not yet boxed is C. So that's 6 plus 4, 10. Okay, we now update it because that's smaller than 13. So C now becomes, okay, so let's have our table again here. So from vertex S, distance of course is 0. So I will put 0 here. This is my current vertex. And the adjacent vertices, wait, I should write down my vertices. I have S, A, B, C, E, F. Okay, all right. Now, my adjacent vertices are A and E. And then let's write the distance. The distance of A from S is 3. And this one here is 4. Correct? So distance of A, 3, E is 4. Previous vertex is S, right? Then what do you do? Choose the smaller number, which is 3, and then you box it. Okay? Now, again, look at the neighbors, which are not yet boxed. So that's B, F, and E. Correct? Okay, so let's see. What would be the distance of E if we pass through A? So that's 3 plus 6, 9. But I already have 4 here. So this remains unchanged. Okay? 3 plus 6 is 9. That's bigger than 4. So just 4 remains here. Next, what about B? So that's 3 plus 2. So the distance is 5. Next, of F, so that's 3 plus 7. So that's 10. Okay, let us now write that. So B5, F is 10. The previous vertex A, 8, right? And then again, we will look at the adjacent. And what will we box? The one with the smallest number. So in this case, that's E. So that's 4. Again, we look at the adjacent vertices. So that's F. F only, right? Because we no longer... Oops, by the way, this is a directed graph. Okay, so am I doing it correctly? Yeah, okay. So meaning to say you cannot go back. You have to follow the arrow. Anyway, Uh, where am I? Okay, so for vertex E, the only vertex, so meaning to say it's not adjacent to A, right? Because this one only. Okay, so that's 10. I mean 10, not F, the vertex F. What will now be the distance? 4 plus 5, so that's 9. So this one gets updated. So this becomes 9. So F here becomes 9 via vertex E. Okay. All right. So, um, again, we look at the numbers, the unboxed numbers. And the smallest now is 5. So we now box 5. Next. Again, we look at the adjacent vertices. Okay, so that's C and F. So here, what will be the distance? So 5 plus 8. So this is now 13. And then here, 5 plus 1 is 6. 6 is smaller than 9. So that means we found a shorter path. Understand? So that becomes 6. So we will now write for C, the distance is 13. Previous vertex is B, right? And then for F, now the distance is 6. I will erase that. So this is 6 and previous vertex of B. Is that clear? Okay. And then again, we look at the smallest number between the smaller number between the unboxed numbers. So in this case, we box 6, right? And then the only remaining adjacent vertex that is not yet boxed is C. So that's 6 plus 4, 10. Okay, we now update it because that's smaller than 13. So C now becomes, okay, so thus here I will change C to 10 via F. F. Okay, so that is now my table. So I was now able to find the distance of all vertices from the vertex S. So for example, what is now the path? The shortest path from S to C. So let us backtrack. So C, previous vertex is F. Previous vertex of F is B, previous vertex of B is A, and the previous vertex of A is S. So where is that? Let me highlight. So that's S, A, B, F, C. Right? So that's 3 plus 2, 5 plus 1, 6 plus 4, 10. Understand? Okay. So first, let us write down the vertices that we have. We have S, A, B, C, E, and F. Of course, we will start at vertex S. So that's 0, distance of 0. And then we will look at the adjacent vertices. So we have A, E, and F. Okay, and then we will write down the distances. So the distance of A is 14, of E is 9, of F is 7. So what will we do? We we now write down their distances from here. So A is 14, E is 9, F is 7. Previous vertex would be S, our current vertex. And then what do? We now choose the smallest number, the vertex closest to S. So in that case, that would be F. So let's box 7. Okay? And then we now look at the vertices adjacent to F. So that's E and C. Take note, I no longer look at S because that's already boxed. We already visited that. So we're just looking at E and C. Okay. So if it's E via F, what would be the distance? So that's 7 plus 10. So that's 17. But that is greater than 9. So I will no longer update this. What about C? So for C, so that's what's the distance? 7 plus 15. So this would be 22. 22. Okay, so wait, let's write that. C, the distance is 22. Previous vertex is F. So now that we're done with our table, we look at our um, the what's this? The smallest, right? The smallest number here, so that's 9, right? So this would now be our current vertex. Okay. And then again, we will look at the vertices adjacent to E that is not yet boxed. So that's A and C. Right? So what would be the distance of A? So that's 9 plus 2, 11. So that means I would have to update A. So this becomes 11. A becomes, here I will erase this. This is now 11, but the previous vertex is E, right? Okay, what else? What about C? So that would be 9, right? So the distance of C via E is 9 plus 11, so that's 20. Aha, 20 is smaller than 22, so I have to update this. So this becomes 20. Then I will also erase this one. So distance is now 20 via vertex E. That's the previous vertex. Okay. And then again, what do we do after finishing the table? We now look at the smallest distance, right? So in this case, that's A, 11. So we box this. We look at the vertices that we haven't visited yet, vertices adjacent to A. So the vertices adjacent to A are B and E, but we have already visited E, so we will not mind that any longer. So we will just look at B. What is now the distance of B from S via A? So it's 11 plus 9. So we get 20. Okay. Now, wait, let me just write that also. 20 via vertex A. Alright. Next, so since we're done, we now look at our smallest distance, but they're both unvisited, right? So for B, let's just choose B. Okay, so for B, what would be the adjacent vertex to that? So that's C. So what would be the distance of C from S via B? Wait, I forgot to box. We're now looking at B, so I should box this. And then again, I'm looking at the neighbors of B that we haven't visited. So that's only C. So the distance of C from S via B is 20 plus 6, 26. So 26 is bigger than 20, so this one would just be retained. Um, I would no longer change that. Okay? And then lastly, so for C, there are no more vertices adjacent to C that we haven't visited yet. So that means that is now the distance. This is the shortest path. Okay? The shortest path would be 20. All right? And so that's it. So for example, what is that 20? For example, let's look at B. What is that shortest path? So for B, previous vertex of B is A, previous vertex of A is E, previous vertex of E is S. So let's look at that. S, E, A, B, right? So from S to E, so that's 9. Plus 2, 11, plus 9, 20. And of course, you can, using this table here, you can again write down all the shortest path of all the different vertices from S. Okay?